come with residues equal to the multiplicity of the polar zero of the original function. So this has a simple pole with residue. It doesn't matter what the residue is. It has a simple pole of order 1. So this function has a pole of order 1 with residue -1, and now it has a residue 1, so that's your x term. So this term gives an x to the 1 over 1 contribution. So this, on the other hand, when we do our computational pole, that's x. That's what x means here. X here means the Riemann zeta function has a pole of order 1 at s equals 1. And then when you pull further, you pick off all of the zeros, including the trivial ones. And again, you have to make this rigorous, so you sum over all the possible zeros, x to the row over row. You have one more thing, which is at s equals 0, this thing gives a contribution, which is of size 1. But never, since nothing I'm writing is accurate anyways. So, all right. So this was story 1, and the moral of story 1 is we now understand that the quote-unquote right way to do number theory is through complex analysis, which seems really counterintuitive. Now, people didn't believe this proof. I mean, people didn't believe complex analysis.
No, it's for hardware and one hardware.
So
it's possible to use everything, to do it completely combinatorially.
So
maybe
that's exactly what I'm getting at.
Okay, good.
So people didn't believe this proof, and they said, why are we going to these complex numbers and continuous integrals and shifting contours? This is something about primes. It should be it's discrete integers. We should be able to find it. And there's, again, the camera's rolling, so I can't tell too many stories about Erdős and Selberg. But there's a there was a quest. It was a long quest to find a quote-unquote elementary, which actually is much harder because it's not. This is very intuitive. You have some function. You found that it has the properties that you want. You pull a contour. You pick up the residues. Done. A quest to find. There's one thing that I'm brushing under the rug, which is how do you actually estimate this stuff away and get something? Well, maybe not that good, but at least that good. You have to know that there aren't any zeros on the one line. That's the extra step. That's what took 40 years from when Riemann stated the conjecture and when it was actually proved, was to show that there are no zeros on this one line. And now if you can show that there are no zeros...
So everything except for this fact, Riemann already had?
Already in Riemann.
And in hindsight, it's completely relative, and geometric identity.
In hindsight, I think I think Conway likes to say every theorem is locally trivial.
No, but I didn't know Riemann did everything except for this.
He had done everything, and he said, I think, he died not long after this paper. He said, I'm going to come back to this topic. He had much more, now that we don't have access to his notes, he had much more information. He didn't say he knew there were many zeros. He didn't say where they were. He had computations of the first couple. This is the Riemann-Siegel formula for computing values. And, but he stated the Riemann hypothesis in this form, maybe with an epsilon, precisely because he understood this contour form and where he believed the zeros were. So you see, if the zeros all have real part a half, then when you put absolute values, all that matters is what the real part of this zero is. And there's your x to the half. Now again, this sum doesn't converge by itself, so you have to, there's more technicalities that you have to be concerned with. But this is just a completely explicit formula, and it's actually really beautiful. So this, if you plot it as a function in x, so let's give this function a name, psi or something. I forget what it's called in literature, probably psi. So here's a function, here's a graph of psi, x, psi of x. Okay, so it's 0 until you hit 2. And once you hit 2, you go up by log of 2. And then when you hit 3, you go up by log of 3. And when you hit 4, you go up by log of 2. And then you hit 5, and you go up by log of 5. Then you hit 6, nothing happens. Because 6 is not a prime power. And you hit 7, it goes up quite a lot. You hit 8, it goes up by log of 2. You hit 9, it goes up by log of 3. You hit 10, nothing happens. You hit 11, it goes up again. In fact, this is why the first zero of zeta is really really high. This first one is at like 14. Because the first few numbers are all primes or prime powers, so it has to keep going up. And now you take x, so here's x, the line y equals x, and then you start adding on these zeros one by one. So you add on the 0 when x is 14, and you see this. And then you add on 2 zeros, and you add on 3 zeros, and it's very quickly becoming, it's a continuous function, but it's very quickly something that you can start to tell with like 5 zeros. You can tell what all the primes and prime powers are by where the jumps are in this continuous function. So this is really something you can see. But again, people didn't have graphing calculators, and they didn't, This is why I say it's the right way of thinking of it. This is the harmonics. These are the harmonics that this function decomposes into in a completely natural way. This is just a bunch of sines and cosines. You just have to put in the right frequencies. Okay. I was actually hoping to tell you a little bit about the Langlands program, but it's okay. We'll go nice and slow. So the quest is to find an elementary proof, and this was accomplished in 1948. What year is the elementary proof? No, 50. 49.
It was published in 1950.
Okay, let's say 48, 49. Erdős, maybe Selberg / Erdős.
Yeah, the paper 1950.
The paper's 1950. Okay. But the events.
Syracuse
What's that?
Syracuse University.
Well, that's where Selberg. Yeah. So there's a long. Yeah. Selberg had a job interview at Rochester, or Syracuse or Rochester. Syracuse. No, the paper's published in Syracuse.
They both worked in Syracuse.
They were at IAS. Selberg went to a job interview. I thought it was Rochester, maybe it was Syracuse. And while he was gone, he had explained what he was doing to Vey or somebody. Vey told Erdős without Selberg's permission. And the great battle ensued. Okay, so another 50 years goes by from the, messy, complex analytic proof until this clean and beautiful, although very long and not at all intuitive, elementary proof using nothing more than divisors and discrete numbers and so on. And this line of research has somehow gone not very far, even though it was expected to be this huge breakthrough. Not a lot has come out of that in the grand scheme of things. Again, I have to be very careful. I'm pretty sure we're not going to be able to use the video because there are lots of people pushing these methods. And this point of view has exploded into a giant industry. So that's kind of the surprise. The surprise is, whatever you think is the right way to do things, a lot more was discovered from looking at L functions and complex numbers and so on. Than the straightforward elementary. Okay.
No, but the Yit and Van is essentially, at least in part, elementary. And
It is in part elementary. He does use the Riemann hypothesis for surfaces at some point.
Yeah. So if you have to use everything you know.
Right. Which I would say, that is coming out of this. I mean, you could say the statements, once you know the statements, wherever they came from, they could be used in other. Yeah. No, it's kind of surprising / embarrassing that Zhang's theorem was proved in 2013 and not 1955. I mean, even Goldstein, Pintz, Yildirim, when they had their huge breakthrough 10 years before Zhang, Selberg was still alive, and he's like, I had these functions on my, in my notes. He didn't do with them what Goldstein and company did with them. Yeah, but so that was a huge success, but maybe not one. This is way. Maybe not one that can be repeated too many times. Whereas this industry has turned into one where we keep finding things. I don't know. Who's to say who's right and who's wrong until The title was something like, why do people doing automorphic forms call themselves number theorists? And this is the foundation of why it started out being number theory and what it has turned into. So let me say a little bit more about what it's turned into. And what it's turned into is basically more functions like this. People have realized that functions like this that have these kinds of properties are very special and very important and can tell you arithmetic things such as the prime number theorem. So let me just very briefly try to tell you some more functions like this and where they came from and how the theory got built up. So one of the beautiful things that Euler did with this observation is in 1737, Euler proved that if you sum over the primes, not 1 and not log, but 1 over p, and sum all the primes, this diverges. He knew the harmonic series diverged, he knew how to sum the squares, but he realized that in fact by the Euler product formula it's very easy to prove this. And for a long time people had been trying to show that in any admissible arithmetic progression there would be infinitely many primes. And 100 years later, it's kind of in hindsight, because the proofs are so similar, you just need harmonic analysis on finite groups. Abelian finite abelian groups. Dirichlet proved the stunning. This gives a new proof of the existence and the infinitude of the primes, but that was known to Euclid, so that's kind of not that striking. But if you sum primes congruent to A mod Q with A and Q co-prime, the reciprocals, this also diverges. This is what Dirichlet proved 100 years later, using, so what he observed, and then you can prove the prime number theorem with progressions. This is some very weak form of a prime number theorem. Dirichlet introduced the so-called Dirichlet L functions, LS chi. So chi is a Dirichlet character. It's a character. So chi is a character of Z mod NZ cross. So that's an abelian multiplicative group. You have a homomorphism from it to the circle, and then you extend it to all of Z mod NZ by all of Z by periodicity and making it 0 on the numbers that aren't co-prime to n. And then you just take chi of n over n dx. Now I would say this is maybe an even bigger break. Well, who knows what's bigger, but the fact that you can put coefficients here and still have all kinds of wonderful properties is another order of magnitude breakthrough. Because what it does is, let's find all functions that look like this. All functions that have a functional equation, an Euler product. This has an Euler product. It's a product over primes 1 minus chi of p over p to the s inverse. And the next family of L functions came, again, 100 years later. Well, there's Dedekind L functions, okay. Maybe not 100 years later. So then there's Dedekind, Dedekind L functions. So these are zeta functions for a field. And then you get Hecke L functions come before Artin L functions, right? Jerry? I think. So you get Hecke L functions. So Hecke discovered the correct analog of, so chi is to Q as a Hecke character, Grossen character is to a number field. So there are L functions attached to Grossen characters. So this is okay. There are more complicated objects. Artin L functions. But they always came in the form you have something nice and arithmetic like a number field, a finite extension of Q, or a character on such, or a Galois representation, or something. And it wasn't until maybe Riemannian, let's say, that the objects attached to these were kind of... That's not really true. The way you prove the functional equation for the Riemann zeta function, let's talk about that for a second. there is an object attached to it, but the objects weren't kind of what people were searching for until the 20th century. So the Langland's philosophy, is that L functions, L because Dirichlet called them L functions, not Langland's, should be attached in a natural way to objects. And now, objects means automorphic objects. And what does automorphic mean? Okay, so how did Riemann prove this functional equation? As I said, Euler did it one s at a time and only the integer values. So you take a theta function. What's a theta function? Let's say you want to study how many ways a number is a sum of two squares, or how many ways can a number be written as a sum of four squares or something. Okay, so here's the natural thing to do. You take e to the 2 pi I n squared z and sum over all integers. So this will be a function of z, say. And then if you take theta to the fourth, well, that's just four summations. So you sum them all together and you get sum over n1, n2, n3, n4, n3 and n4, e to the 2 pi I z times n1 squared plus n2 squared plus n3 squared plus n4 squared. So if you combine this together, you get a sum over some integer m, let's say, e to the 2 pi I m. And how often does m arise? How often is m the sum of four squares? That's R4 of m. Is the number of representations of m is a sum of four squares. Okay. So if you want to analytically estimate this, there are all kinds of methods to studying this thing. But you could, integrate out, what happened to z? Z. You could integrate out z, pick off the mth Fourier coefficient of z, and that tells you this value. Okay. Now this function has some very special properties. For one, it's invariant under z goes to z plus 1, right? It lives on the circle. In fact, the first thing that you should be concerned about is, does it even converge? And if z is a real number, these are all things of absolute value 1, so there's no chance of convergence. So, but if you take z in the upper, make z a complex number, and take it having imaginary part positive, then you have an I and another I, which gives you a negative I. Now you have exponential convergence, and everything's good. So now people are studying functions on the upper half plane with nice symmetries. One symmetry is z goes to z plus 1. Another thing you can see is that if z is, if you replace z by minus 1 over z, or really minus 1 over 4z or something, so there's something like z goes to minus 1 over z symmetry, and the group that generates, the group generated by these two symmetries is isomorphic to the group SL2z. So now you get into, so this is actually a half integral weight. So this theta series is a half integral. The real theory of these things wasn't kind of codified until Shimura in the 1950s and 60s, weight modular form. But when you raise it to the fourth power, you get a weight 2 form. And if you express this weight 2 form in terms of things called Eigenstein Series, you can read off these Fourier coefficients from the Eigenstein Series. That's essentially how they didn't call, well, they kind of did call them this way in the early 1800s or something. Okay, so the point is you need to find automorphic objects that are attached to L functions. And how do you get an L function out of this? Well, you integrate. Again, it's another integral. How am I supposed to get the zeta function out of the theta function? It's really all this business is. It's a bunch of cute integrals that come out and give you connections between things. So what if I integrate over the vertical line from 0 to I infinity in the upper half plane? I take the Mellin transform in this case. I take theta of Iy, and I'll raise y to some power, y to the s, dy, and I'll take the hyperbolic measure from 0 to infinity. What do we get? Well, we have a problem because if n equals 0, then this is the constant function. You can't integrate a polynomial from 0 to infinity. So let's take away the constant function. So now I have n not, so if I take away 1, then I have n not equal to 0. And there's an n squared here, so we get a contribution with positive and negatives giving you the same thing. So if I divide this by 2, I could just take n to be strictly greater than 0, which is the same as greater than or equal to 1. So instead of theta, what I really want to take is theta minus 1 over 2. Okay, which has very easy invariance properties, because we know what the invariance properties of the original thing. Okay, let's plug in what the series is. So it's a sum, n greater than or equal to 1. I have my integral from 0 to infinity. E to the, now z is iy. Z is iy, so I get minus 2 pi n squared y. Right? And then a y to the s, and a dy over y. So far, so good. And now I make a change of variables. Y goes to y over, I'll send y to y over 2 pi n squared. So when I do that, this cancels. I get an over 2 pi n squared to the s. dy over y remains the same. The range of integration remains the same. And the beautiful thing is this just comes out in front. And there's no more n in the integral. So you've completely separated out. So what you see is a sum over n greater than or equal to 1. 1 over 2 pi to the s. In fact, that can pull all the way out. 1 over n to the 2s. And what's left here is an e to the minus y, y to the s, dy over y, which is your gamma function, gamma of s. In fact, this is nothing more than this completed zeta. At 2s. Minus 1. I'm sorry. Okay. So, let's wrap up. What's the Langlands program? Let me tell you the Langlands program in one line. Okay? If you know a bunch of coefficients that make a nice L function, where are my L functions? I've erased the top. If you know these numbers, and they have nice properties, when you put them into some kind of series, like a Q series, does that have nice properties? So that's why I was thinking about, when I was thinking about this, I started thinking about these meanders. Maybe the meanders are a weak harmonic Moss form. And so here's the Langlands program in one line. Tell me why this function has an invariance under x goes to x plus 1, x plus 2 pi. Question, why, so let's call it f of x, why is f of x the same as f of x plus 2 pi? That's the Langlands program.
Obvious.
It's obvious.
But it's got the cosine function. So we know.
If you know that it's the cosine function, then it's obvious. It's very easy to go from the cosine function to its series, and you know the invariance of the cosine function. But if someone hands you the series, this is what happens. When someone hands you a natural series, like the symmetric nth power representation, does it have some nice invariance properties?
So you have a lemma, this is like differential equation, and that was number
In this case, everything is known. The generalization of this, and it's not a very hard generalization, you can write down something with the Riemanns tau function and say, does it have some nice invariance? And that's an unsolved problem. Okay, so.
Thank you very much.